Here's another min-max problem. This one's slightly more complicated. A company wants to make a 1 litre or 1,000 cubic centimetre cans of fruit. What dimensions minimize the metal needed? So here, what we're really interested in is the volume has to be equal to that. The surface area is what we're trying to minimize. So let's again just have a little diagram just to help us. So the dimensions here we really have control over is we could choose the radius that we're going to make the cans. We could use diameter, but radius is going to turn out to be easier, and the height. So the volume, if we remember back to our year 9 maths, is going to be pi r squared. So that's the area of the end times by the height. And we want that to equal 1,000 cubic centimeters. We're going to use the units of centimeters here. Now I'm going to rearrange this now just because it's a little bit easier, but I could do it later. I'm going to make it h equals 1,000 over pi r squared. I'll make the h the subject because in a moment you'll see that this is the easier way to go. Now I'm going to just use a for surface area. Now again, going back to our year 9 maths, I've got the two ends. And each of those is each of those are pi r squared, so there's two of them. And then the area of the middle bit, if we unfold, it becomes a rectangle of height h, and the length is the circumference of the circle, which is 2 pi r, and then we've got the h. And that's what we're trying to minimize. So I currently got two variables, my r and my h. By substituting that in, I can get rid of one of those variables. So 2 pi r squared plus 2 pi r, replacing the h with 1,000 pi r squared. Now we can do a little bit of simplifying here. The pi's disappear, one of the r's disappear, and I can times the 2 by 1,000. So 2 pi r squared plus 2,000 over r. But because I'm about to derive this, I'm going to say it's r to the minus 1. So now to find my minimum here, well, I want to look at any stationary points, and I want to look at any end points for this. And we'll get back to looking at the end points in a moment. So let's just do my derivative. So derivative of 2 pi r squared in respect to r, we've got bring the 2 down the front, so 2 times 2 is 4. Reduce the power by 1, r. Now here I want to bring the power out the front, so minus 1 times 2,000, just minus 2,000, and reduce the power by 1. And I want that to equal 0 to find my stationary points. So a little bit of rearranging. I'm going to add this lot to both sides. So 4 pi r equals 2,000, and I'll put the r back on the bottom. So now timesing both sides by r, and I'm going to divide by 4 pi. We might just finish that off on the next page. I can probably put it over here. So r equals the cube root of whatever this is. If I put that in my calculator, I find that my stationary point is when r equals 5.42 centimeters to the nearest two decimal places. Okay, so I'm interested in that point, but I'm also interested in any points that will, any endpoints. Now this one doesn't have any, because I've got a volume. If I increase my height more and more and more, I end up with something that's really tiny and thin, but I'm never going to get to a point that there's a natural endpoint for this. Or if I increase my r hugely, I get something flat, disc-like. The height's really low, but again, it never reaches any endpoint. That's because I've got this r to the minus 1 in here. So it has asymptotes.